Yeah. So
Yeah.
I can start, right? First of all, so today I'm going to speak about like reflexive spaces. As an overview, the theorems that are going to be there is like first, suppose L is a linear function on the non-linear space H, then L is bounded if and only if kernel L is closed. So this is one theorem, and so after that, then we move on to the main topics like so isometric embedding in the bidual. So if H is a non-linear space, and if phi h is a functional phi h is a map evaluation map given by phi h of L is equal to L of H, then the map H going to phi h is an isometric embedding of H in H double star. And H is called reflexive if H is equal to H double star through the above embedding. And a Banach space H is and we also present I also present one theorem and its corollary. A Banach space H is reflexive if and only if H star is reflexive, and a corollary is that all this inclusion, it's contained in its by double star and so on. These are all strict if H is not reflexive. Yeah. To start with it, so first we try to prove the theorem we mentioned. So if L is a linear functional, uh, then L is bounded if and only if kernel is L is closed. So if L is bounded, then it is continuous for the forward direction. So kernel L is L inverse 0, and thus kernel L is closed. Zeros are closed set. For the other direction, uh, suppose kernel L is closed, then what we have is if kernel L is the whole space, the L is the zero operator, and we have it is definitely bounded. So we can assume that kernel is not whole of H. So let H belongs to let H be a point outside kernel L. Then L of H is not zero. We can replace H by H model H H by L of H, and if needed, and we can assume that L of H is equal to 1. Since kernel is closed, we can find a open wall around H that doesn't intersect with kernel. So what I'm saying is, if y is an arbitrary point outside kernel L, then x minus y by L of y is contained in kernel, because L of x is 1 and L of y by L of y is again 1. So L of the whole thing is going to be 0. So since it is contained in kernel and this ball was disjoint from kernel, so we have that this is not contained in this ball. Um, Thus, this inequality holds. X minus y by L of I minus h is greater than or equal to r. Norm of that is greater than or equal to r. So we have this inequality, and from that we get that L is bounded because L of y is less than or equal to 1 by r times y. Okay. So what happens is we get that this inequality holds for every y not in kernel of L, and for y in kernel of L, this is true because L is 0 there in kernel L. Yeah. So we get that L is bounded. So the theorem is proved. Like L is bounded if and only if kernel L is closed. Uh, okay. So yeah. So now for the embedding of H in H double star. So phi h be the evaluation map, L going to L of h, where L is in H star. So this is a linear map, and also uh, since L is bounded, we have that phi h of L is, which is L of h, have the modulus less than or equal to norm of L times norm of H because L is bounded. So since this is true for any L, we have that phi H is a boundary operator, and thus phi H belongs to H double star. So what I'm saying is the map given by H going to phi H is an embedding in the bidual. So where phi H is the map mentioned here, an isometric embedding. To prove that, phi is linear first because phi of alpha H plus y uh, of L is going to be L of alpha H plus y, and since L is linear, we easily get that this is going to be equal to alpha times phi of H plus phi of y, like at L. So phi is we can see that the map is linear, and we also we have to show that it is an isometry. So for that, uh, here we showed that phi h of L is less than or equal to L norm of L times norm of H. From that we get that norm of phi h is less than or equal to norm of H. And by Hahn-Banach theorem, there exists some L dash in H star such that L dash of H is equal to norm of H by a corollary of Hahn-Banach theorem. Thus, we get that this this is actually equality. Phi H is equal to norm of phi H is equal to norm of H. Yeah. So about reflexive spaces, a space H is called reflexive if H is equal to H double star. The H is equal to the bidual through that embedding phi. Uh, and the theorem we present is a Banach space H is reflexive if and only if H star is reflexive. So for the forward direction, suppose H is equal to H double star. I mean, if H is reflexive, then we have to show that H star is reflexive. That is, we have to show that this inclusion is actually an inequality. So we just have to show the surjectivity because like we already proved that it's an embedding. So suppose lambda belongs to H triple star. We have to find some L such that lambda is equal to psi L, where psi is the this embedding. Now, if Z belongs to H double star, then Z is equal to some phi H, where H belongs to H, because H is reflexive. And what we can say is we can say that L of H is equal to, we can define L of H as lambda of phi H. Okay, so again, absolute value of L of H is equal to absolute value of this, which is less than or equal to norm of lambda times norm of phi H. And this norm of phi H is actually norm of H because of reflexivity. And thus we have that L is bounded and thus L belongs to H star. So we have that L belongs to H star. We are claiming that psi L is actually lambda. To prove that, psi L of phi H is equal to phi H at L, which is equal to L of H. And this by definition is lambda of phi H. And since phi was surjective because of reflexivity, we have that lambda is equal to psi L. Thus, we got that embedding psi is a surjective map and H star is equal to H triple star. Now for the other direction, we can assume that H star is reflexive. Again, this is an embedding. We just have to show the surjectivity. So suppose this was not a surjective, if the embedding was not surjective, then by a corollary of Hahn-Banach theorem again, like there exists a lambda in H triple star such that lambda is non-zero, but lambda restricted to phi h is 0. So what but we have that this lambda is an H triple star, and by this equality we get that lambda is equal to psi L for some L in H star. So
Once again, this Hanma, this is that closed?
yeah, because this was an isometry actually. So because of that we have that phi of H is closed in H triple star.
Oh, that makes really good. Because that's for closed subspaces.
Yeah. Okay, we are using the fact that this one is an isometry there. Uh, yeah. So lambda is equal to psi L for some L belongs to H star. Uh, Thus, lambda phi h is going to be psi L times phi h, which is phi h L, phi h of L equal to L of h. Uh, so we know that lambda restricted to phi h is 0. So L is equal to 0 from this thing because of this thing. Uh, Thus, since L is equal to 0, we have phi L is equal to 0, and thus lambda is equal to 0, contradicting lambda is non-zero. So, again, our assumption is wrong. The embedding is surjective. S is equal to S double star. So, the final thing is like we have a corollary of this theorem here. Uh, the corollary is that if H is not reflexive, then all these inclusions they are all strict. So to prove that, so suppose not, like if at some point n greater than or equal to 1 we have that like n, like h star n, I'm representing like n times dual as h star n. So h star, if h star n is equal to h star n plus 2 at some n greater than or equal to 1, then this means that uh, um, h star n minus 1 is equal to h star n plus 1, because h star n is equal to h star n minus 1 star. So by this thing, by this deduction of this theorem, like if h star is reflexive, then that means that h is reflexive. We have that h star of n minus 1 is equal to h star n plus 1. By continuing this, by induction, we can get that h is equal to h double star. So h is reflexive, contradicting this thing. Yeah. So that is the corollary. So all the inclusions must be strict. Yeah. Yeah. That is it. Thank you.
Very, very soon. So, any questions? Okay. So, with this, the course ends. And, let's stop recording.